think after you finish your PhD, you don't remain a student member. I think you become a member. So I think you can't be a part of a student branch chapter. I think it's something like that. I'm not really sure, but I think might be something like that.
But then, I mean, new members would enter, no?
Yeah. Not even full 3 years have been completed. So last year we applied for DMail. Our previous chair, Ordhendu Kundu, he applied for DMails, and this time we got the DMLs for 2021. So maybe this year again we will apply and we will get for 2022.
Interesting. Are faculty members involved here as well?
Yeah, actually, we have our faculty advisor is Professor Bhaskar Gupta. I think he's in the chat, right? I mean, he's in the meeting right now. So maybe before we start, he can say a few words.
Sure.
Yeah.
Honestly, he was not like I mean, he was like a non-playing captain, and and I think everybody knew Solomon Anti, but the other person I forget the name, Chatterjee Chokro, something like that.
Yeah.
Yeah, it was a funny times actually. This is before cell phones, right? So I think
yes.
The world before cell phones and after cell phones is pretty different. Even like 6-7 years later, it sort of changed.
Absolutely.
It was an interesting time.
Yeah, well,
so who's
the
principal now? I mean, who was the principal when you were there?
I think it was the same principal who you talked about. I don't remember her name, but we all remember Solomon because I think that white hair and her figure was very, we remember. We tend to remember. Yeah.
And who taught you physics at in your class 11-12?
Physics was taught by many teachers actually. There was Partho sir, and there was PPR. PPR had just come back from America, I think, and he used to tell us that he was some a fellow of some society in America or something. Every day he used to remind us. And there were a few teachers as well. There were a few newcomers as well. So maybe you don't know about them. They joined pretty, I think, after you left. So yeah, but yeah, we had good teachers.
Very good teacher, Molla Roy.
Yeah.
He became, I think now he's a professor in Shibpur, I think.
Okay.
He did PhD later on, but he was, I mean, by far head and shoulders above the rest. Yeah, PPA was that, and then we had Joydeep sir too.
Yes. Joydeep sir did not take our classes, but yes, we took some other section.
Interesting.
Okay, so I think we can start. It's 7:06. So
sure, absolutely, yeah.
Yeah. So before I start, a very warm welcome to everyone present. We have a pretty global audience today. Thank you for joining us for this webinar. So before I start, maybe Professor Bhaskar Gupta would like to say a few words. I think he's in this meet. Okay, so maybe he's not available right now. Let me just start, and maybe when he's available, he can say a few words. So, as you all know, the topic of the webinar is towards universally programmable chip-scale THz source sensors and systems, bridging the THz and application gap in the next decade. And it will be presented by Dr. Kaushik Sengupta. So, without further ado, let me introduce the speaker. Kaushik Sengupta received the BTech and MTech degrees in Electronics and Electrical Communication Engineering from IIT Kharagpur, India in 2007, and the MS and PhD degrees in Electrical Engineering from the California Institute of Technology, Caltech, Pasadena, CA, USA in 2008 and 2012 respectively. In 2013, he joined the Department of Electrical Engineering, Princeton University, Princeton, New Jersey, USA as a faculty member. His current research interests include high-frequency ICs, electromagnetics, and optics for various applications in sensing, imaging, and high-speed communication. Dr. Sengupta received the Bell Labs Prize 2017, Young Investigator Program Award from the Office of Naval Research in 2017, the DARPA Young Faculty Award in 2018, and the E. Lawrence Keyes Jr. / Emerson Electrical Company Junior Faculty Award. He was 6 times selected to the Princeton Engineering Commendation List for Outstanding Teaching in 2014, 16, and from 2017 all the way to 2020, and received the Excellence in Teaching Award from the School of Engineering, Princeton University in 2018, nominated by the Undergraduate and Engineering and Graduate Student Council. He is currently serving as a steering committee member of IMS 2021, as workshop co-chair, and as a member of the MTT4 committee on THz technology, and has served on the technical program committee of the IEEE ESS CIRC, IEEE CICC, IEEE ICC, and peers. He is co-recipient of the 2015 MTTS Microwave Prize. He is currently serving as a distinguished lecturer for IEEE Solid State Circuit Society 2019-20, and will serve as a distinguished lecturer for IEEE Microwave Theory and Take 2021.
In terms of economic opportunities, startups, and things of that nature, this is a really, really exciting area to be in. I'd like this to be interactive, even though I can't see anybody. And if you do have questions, just unmute yourself, ask a question. I think that if it's interactive, it's more interesting. So before I go, I have to present the slides, which is basically advertisement for MTTS. And that's very important because MTTS is, I believe, one of the largest IEEE societies and one of the oldest as well. They call it the megahertz to terahertz. And so if you are not an IEEE and MTTS member, please become one. There are plenty of opportunities in terms of networking, career building workshops, learning various tutorials, things of that nature. And of course, IMS this year is going to be virtual. So if you have not attended IMS because previously you had to come to US, you can now attend IMS from your home, wherever you are. And so please do consider, joining IMS for the virtual conference if you have not already thought about it. The MTTS publications essentially are the top notch in the field. So there is obviously the magazine and the transactions and the THz Science and Technology. There are multiple transactions. So again, you would be exposed to a wide range of top class research being published in this space. And of course, that also means that you're also part of big conferences like IMS that's happening in June. So again, because it's going virtual this year, do take advantage of it. It was virtual last year as well, but this year is going to be virtual. We don't know what's going to happen next year, but since it's completely virtual, there's a part which is completely virtual this year. Please do consider joining it. Of course, the MTTS also gives you opportunities for local events and conferences and so on and so forth. So with that, let me begin my talk. Okay. So if you think about the wireless connectivity and all the hype that's happening around 5G, now people are talking about 6G, whatnot. There is some, real meat to it. It is not just hype. And the reason I say that is because we are really at an inflection point in wireless communication. So if you think about, what are the generations of wireless communication that, we have covered, it's the field itself is not new, right? It's at least 100 years old. So, but if you look at the first generation of wireless communication, right? So this is basically a Tesla power plant, but the idea there was that back in the days, maybe 100 years ago, there used to be a tower-to-tower communication. This was like Marconi with Morse codes and spark plugs. A tower could send information to another tower. Okay, so this is exactly how Titanic was saved. For example, they could send an SOS message from their ship to another ship. Okay, so it's between towers and towers. The second generation of wireless communication was from tower to people when radio came. So as an example, this was used by a lot by politicians of the day, and this is FDR, Roosevelt, who used to spread his messages through radio because it used to be beaming at everybody's home. So it was tower to people. We are basically now in people to people, right? You can call anybody, I can talk to you. So every person can talk to any other person in the world. And so if you think about how many people are there in the world, it's billions, right? So in terms of networks of nodes connectivity serving the endpoint users is of the nature of billions. What's happening in the next 10 years is that the idea is that it's moving from people to everything to everything. So your car is going to be connected to your fridge is going to be connected to your home is going to be connected to your thermostat. It's all gadgets that have sensors and decision-making capabilities would be connected by internet. Now, these internet connectivity would have very, very different requirements. For example, your car connectivity would have very different requirements than your smart home connectivity. And so the idea here is that how would this sustain, right? We don't have the bandwidth at the low frequency regime that we typically use, Wi-Fi, cell phones, things of that nature, to sustain this enormous increase in capacity. So what's happening is that a new spectrum is opening up in a way that it's becoming commercially available in a way that was not happened before. And this kind of spectrum is what we call the millimeter wave and the higher frequency. And I'm going to loosely refer anything above 100 gigahertz in terahertz, though the community sometimes refers anything above 300 gigahertz at terahertz, but I'm going to loosely define that way. So this 10 to 100 plus gigahertz is becoming available in multiple bands for commercial use. That includes new bands in satellite communication, that includes new band in 5G and so on and so forth. New bands in unlicensed and shared spectrum, which is a 57 to 64 gigahertz bands. Okay, so these are the kind of bands that people have, the military used to use at some point for radars in many of these applications, but now it's becoming commercially usable. We already have 28 gigahertz cell phones. The iPhone 12, 5G. I mean, has a 28 gigahertz phased array inside the phone and can connect to a 28 gigahertz tower. Why do you need 28 gigahertz tower? Because then you get a 400 to 800 megahertz bandwidth sustaining multi-gigabit per second data. Okay, so multi-gigabit per second essentially means a Netflix movie in 1 second. Right, so that's the kind of speed we are talking about here. So one of the reasons there's also the economic side of things. The economic side of things is that spectrum is the costliest real estate in the world. So if you have not followed 5G spectrum auctions, think about it. You own the spectrum. As a person living in any country, spectrum is a shared resource. So every one of you has some ownership of the shared resource, which is spectrum. And spectrums are auctioned to companies. So as an example, I think a couple of months ago, 5G spectrum was auctioned in US. And the cost of per megahertz 5G spectrum, they were looking at the C-band. This is what we call the sub-6 gigahertz 5G, is around $160 million per megahertz. And we're talking about around 500 megahertz. So they basically raised around $80 billion, right? In India, the cost is around half, but it's still substantial, 500 crores per megahertz India, right? So it's a very, very costly resource. So that's what's happening. And so there's always a tendency to move to a higher part of the millimeter wave spectrum, which is here between 28, 39 gigahertz and beyond. So you can see that these kind of bands are opening up in Europe, Latin America, China, South Korea, India, everywhere else, allowing millimeter wave connectivity, high-speed connectivity, low latency connectivity that in a way that you couldn't do before. So what are the other applications? So communication is one example of it, but it's not the only example, right? So these high-frequency waves have smaller wavelengths. And if you have smaller wavelengths, you have higher resolution in sensing and imaging. So for example, most of the cars these days, a lot of cars here, at least in the United States, have low-cost radars. These radars used to be, $20,000, $30,000 20 years ago. Now they're $100, $100. And so you can buy these radars operating at 77 gigahertz from commercial companies. And now many low-cost cars will now have radar of autonomous vehicles or autonomous driving capability. You can imagine applications in drones, for example, drones communicating between each other. Augmented and virtual reality applications, right? So there's a lot of work going on in sort of Facebook and other places where they're looking at wireless, connectivity for augmented virtual reality. Now, the amount of data and bandwidth you need for this application is tremendous. And therefore, to support that, you need to move to higher frequencies. For sensing applications, so here I'm showing a Google Solly project where you're basically picking up tiny gestures from your fingers from a cell phone, right? So you're not pressing a button, but you're gesturing tiny twitches that can be picked up. And the reason they can be picked up is because of higher frequency, because higher frequency gives you the resolution that you need for tiny finger movements. Here they're using around 60 gigahertz radar. So the radar is inside the object here. And so with the 60 gigahertz radars, you can pick up sort of millimeter scale movement of your fingers. This is a picture of from NASA using 675 gigahertz for standoff imaging for a person carrying guns. So there's a lot of interesting applications from 30 gigahertz to 1,000 gigahertz in terms of sensing, imaging capabilities that we couldn't do before to enable the kind of smart environment that we are thinking about. In communication, there's a lot of interest applications as well. So as I already mentioned, the millimeter wave 5G cell phones and cellular connectivity that you need. But there's also applications in backhaul. So if you know that your tower of your cell phone is providing you data, right? But the data has to come from somewhere. So where is it coming from? It's typically an optical fiber that is going to a data center that somewhere else is located. Well, sometimes it's very hard to dig up roads and mountains and lay up these optical fiber cables. So wireless backhaul could also be an interesting method of a high-speed connectivity. Now, these optical fibers have very, very high bandwidths. So your wireless needs to have very, very high bandwidth, which essentially means that you have to move to higher frequencies. So you can imagine that you can deploy these wireless backhauls connectivity to allow internet connectivity to places where you couldn't do before. So as an example, if you don't know this, if you take the whole Earth population, around 50% don't have internet connectivity. But most of them are located at least within very close location of a nearest tower. So if you could bridge the last mile connectivity, you would bring additional 50% people into an internet connectivity. And as you know, internet connectivity is basically the economic engine of tomorrow, right? So what do you need from these, right? So if you think about these kind of high frequency waves, one of the basic requirements of that is beamforming, which is unlike low frequency, you cannot send the waves to everywhere like your cell phone does, like your cell phone towers does, and think about the cell phone is just going to pick up a little bit of it. Here, the path loss for the same aperture gain is proportional to the frequency square, which essentially means that if you're going from 3 gigahertz to 30 gigahertz, you're going for a fraction of 10x in frequency. That's 100x more in loss. So essentially what you need to do is you cannot afford the power to be everywhere. So you need to behave almost like a laser. It's like a beam that you need to generate. And so if you have a beam that you need to generate, you could be pointing to your user. So as an example, on the picture on the right-hand side, this is shown as a pictorial. So if your cell phone is located, this tower is going to beam a very narrow beam to the tower. So the most of the energy is focused to the for the cell phone. Now, of course, these are not static beams. These are dynamic beams. So if the person is moving or the car is moving, the beam needs to track. And so the technology of that is what we call the phased array, right? So phased arrays are antenna arrays that control the amplitude and the phase of the different antenna excitation. So these circles represent a 2D antenna array. And by controlling the amplitude and phase, you can create multiple beams. You can electronically track the beams at very high speed. Phased arrays has been there in defense for a long, long time. It's not a new concept. So these are examples of phased arrays already deployed for missile detection. It's in jet fighter engines. These are some of these are low frequencies, some of them are high frequencies. So example, this was I think a missile defense monitoring system, right? So you can imagine each of these is an antenna, right? So you can imagine how much of information can you get from so many antennas laid out on the surface. For a high frequency, right? This is, for example, X-band radar in a Raytheon F-18 engine. So this is the size of the radar. And of course, the spacing of the antenna is a function of the frequency. So higher the frequency, smaller is the spacing. So now at very, very high frequency, the antenna spacings are very tiny, and therefore you can make phased arrays very compact. Now, these are very expensive phased arrays. You're not going to have, a very expensive phased arrays in your cell phones. No one's going to buy that, right? So these are based on what we call the gallium arsenide TR modules, right? So you would basically build these, complex TR modules with some monolith integration, some PCB. You would have to package it, and then each becomes TR module. Then you have a switch, you connect your antenna, and the cost and the time and the testing of this fabrication is enormous, which is why these things cost money. What has happened in the last, I would say, 15 years is that phased arrays are having a transformation in terms of technology through Moore's law. And so you probably have heard of Moore's law. The idea of Moore's law is that the integration capability of silicon ICs are growing every generation, essentially doubling every 18 months, right? So Moore's law sort of tapered down in the last, I would say, 10 years. But if you look at where we have come from silicon IC integration, it's incredible. So this is the first planar IC, 1960. It's 1 bit of memory. The whole wafer has 1 bit, not 1 kilobyte or gigabyte, just 1 bit. Okay, it's 3 to 4 transistors. And now you have, if you buy an NVIDIA graphics processor, there's 21 billion transistors directly integrated in the chip. I mean, that's, if Earth's population is 7 billion, that's like 3 times Earth's population inside one chip, right? And then all of these transistors work. So in terms of absolute, enormous integration capability, I mean, this is really an amazing invention that has gone through lots of changes. In terms of cost, the other thing is cost, right? 100 million transistors you can integrate in 1 millimeter square for $1 in volume production. So in terms of cost, you can see that you can have the power of 100 million transistors within a 1 millimeter square of silicon ICs these days for $1 in volume production. So this is an enormous, this is a technology that what has happened is from computation, we are now moving to communication. And high frequency communication. So as an example, this was one of the earliest sort of transmitter base stations. This is a megawatt pulse and arc radio transmitter in 1917. I mean, look at the person there. I mean, you could die if something goes wrong here, right? And look at the generations, what has happened since then. These are the kind of 28 gigahertz phased arrays from IBM, 100 gigahertz phased arrays from Nokia Bell Labs. And look at the size of these things, right? You can have, these are fully integrated phased arrays. These are antennas, okay? So these are antennas. There's a silicon chip at the back end. You can control all the antennas. You can get all the data. You can process the data. And now what you have is a Lego piece. You can build larger scale phased arrays with these Lego pieces. So that is the direction where the things are going. That is the direction where you can make phased arrays low cost and really complex phased arrays very cheap. In the millimeter wave and terahertz, this is not a new thing. One of the earliest works in millimeter wave integrated phased arrays in silicon came from our group at Caltech back in like 2004, 2006. Like this is before my PhD. But they were doing 24 gigahertz, 77 gigahertz. Berkeley was doing a 60 gigahertz phased arrays in 2006 at the time, and they had a company from there. And so this has been demonstrated way 15 years ago that this could be done. But now with the 5G and the frequency allocations, the commercial use cases are enormous. This was actually part of my PhD thesis. We demonstrated the first terahertz phased array above 300 gigahertz, close to 300 gigahertz. So this was a single chip system, which essentially beamforms at close to 280 gigahertz. And it's electronic controllable, so you can do beamforming in either directions and so on and so forth. Space is another applications, right? So, India is doing amazing work in the space area because of ISRO, but space is, getting a lot more attention because of its applications in connectivity and national security and so on and so forth. So this is another frontier right now, right? I mean, now if you pick up a Starlink, which is what, SpaceX is trying to put up, this is a Starlink X-band, satellite dish antenna. right? And I would recommend you to take look at the tear down of this. So if you take this down, right, and this is a zoomed version of these, you can see, I don't know if I have, but you can see the antennas here, right? You can see the antennas here, and each of them is connected to tiny sort of silicon ICs. So this is entirely built off silicon ICs, and used as Lego pieces to build the whole structure. I mean, this is enormously complex, but you can now imagine you can get silicon ICs, you can build these things, there's packaging of the antennas involved, and so it is essentially an end-to-end system work that's making these things happen. Okay, and there's a lot of opportunities here to have really significant contribution here. So as an example, we don't know how to make this low cost. I mean, these are still expensive stuff because you need so many silicon ICs, you need so many antennas, the packaging has to be very nice, and so on and so forth to make these satellite dish antennas. But lots of startups have come up trying to make these work at low cost now. And so, given that's the background, let me just give you a sense of what we do in this space. Of course, these are being done by commercial companies. So what are we doing here, which is different, right? And so just to give you an introduction, we have two directions in our lab. I mean, obviously, I'm going to focus on one of them, which is the millimeter wave terahertz, especially terahertz, not even the millimeter wave. But we also work on biosensing and medical diagnostics and things of that nature. So if any of you are interested, I'll be happy to chat with you after that. But I'm not going to present any of that. I'm also not going to talk about our work in the millimeter wave, but only focus on higher frequencies above 100 gigahertz. Okay, so this is our lab, by the way. I mean, it's a very multidisciplinary, multicultural, multi-country, multi-gender, multi-ethnicity lab. This is a little older picture, 3 years ago, but you can see that there are people all over the world from here. Everyone's smiling, so everyone's happy what they're doing. Hopefully that's the case. And if you are in sort of New Jersey or the East Coast area, do send me an email. Would be happy to show you on the campus. The campus is really nice at Princeton. Okay, so given that's the background, let me just tell you some of the backstories and how we are thinking about systems at these high frequencies. So this is a Nature Electronics paper that we were invited to write with some of my collaborators, Professor Nagatsuma from Osaka University in Japan, and then Professor Mittelman from Brown in the USA. And we were basically talking about how the terahertz space has fundamentally changed in the last 10 years. And the idea is that people in space astronomy has been looking at terahertz for a long time. For example, cosmic microwave background radiation happens at frequencies above 100 gigahertz. So they have been looking at these frequencies for a long time. In the last 10 years, we now can do these systems at low cost with chip scale systems and their commercial applications. So that's the difference. The space was typically called the terahertz gap, the terahertz spectrum. And so this is a picture from Nature Photonics article in 2007. And it was basically saying, look, this is frequency, this is power, terahertz is somewhere here, and there's hardly any technology that can generate power. So you can see the power basically falls down dramatically at high frequencies. And so that idea was, this is why it's called the terahertz gap. Okay. If you notice the red dot here, this is the first two works that demonstrated power generation in terahertz in silicon ICs above 300 gigahertz. This was in 2008.
Excuse me, 1 second, Dr. Sengupta, can you just hide that icon showing stop sharing hide? Can you just hide it? Because people are saying that there's some info. Yes, thank you very much. Please continue. Sorry for interrupting.
Yeah, no, thanks. And so what has happened is this picture has sort of transformed in the last 10 years. And what does it look like now? And so if you want to get this picture, you can read this article. You see that the space has filled up, right? RTDs, or resonant tunnel diodes, they have improved in the last 10 years. Photo mixers have improved. MMICs have improved. All of these things have improved. But what is interesting is that the silicon terahertz, which was 2008, somewhere here, and 2018 was somewhere there. And this is in log scale, right? So you can see the amount of improvement, almost like a million-fold improvement in power generation ability with silicon chips at these high frequencies. So this is what we call the inflection point in sort of terahertz in chip scale systems in the last decade. Okay, so given the fact that we've already done that, what's the future, right? So what are we doing here? So what we are proposing in that paper was you need to go beyond just generation of power and detection of power to make useful systems. So think about the use cases, right? So think about a system like this, right? So this is what you're seeing here is basically a car moving through a street, an autonomous car. And they're using multiple sensor devices. So one could be radars, one is LiDAR, one is camera, and it's a collection of all these images that's enabling you to understand what your environment is. So if you see the white dots here on the top, those are the LiDAR reflections. So LiDAR is basically radar optical frequencies. But there's a millimeter wave radar. There is also an optical camera. So the idea is that you get information from different portions of the electromagnetic spectrum because they'll give you different information, and then you fuse it together to get a better understanding of your environment. If you're driving through fog, for example, your camera is not going to work. You're going to bump into the next car. What's going to work in a fog? Your LiDAR is not going to work in a fog. So your radar, your millimeter wave radar will work in a fog. In some cases, your millimeter wave radar is not going to work, so your optical camera is going to work. So combining the information across multiple spectrum is essential to this kind of complex sensor fusion. So what we were proposing is that we need to now move terahertz from just demonstrating that it can generate power and can receive power to allow programmability, to allow adaptability of these systems depending on what they are working on. And so if you think about a THz source, what is it generating? It is generating a THz field at some point, right? And what are the properties of a THz field, of any electromagnetic fields? It is basically spatial distribution. So if it's radiated fields, spatial distribution, polarization, and spectrum, right? What is a THz sensor doing? It's getting the power or amplitude and phase from an incident field. So what are the programmability of a THz sensor? Again, polarization, ability to work across the spectrum, and ability to work across different angles of incidence. So this would be what we call the holy grail of THz sources and sensors. We don't have a technology that can do that. There's no source technology that can generate 100 gigahertz and you can just program it to generate 300 gigahertz. There's nothing that exists. Even generation of 300 gigahertz itself is tough. So enabling programmability on top of a hard problem is even harder, right? So then the question is, what are the challenges here, and how we can think about approaching the system? And I'll try to give you some examples here. Okay, what is the first challenge? Some of you may be in circuit, some of you may not be in circuit. So this is basically showing a device and a parameter, what we call Fmax. So what is Fmax? Fmax basically tells you what is the maximum frequency where the device can ideally amplify. Amplifiers are fundamental to any transceiver, right? So it basically tells you that above a particular frequency, it won't amplify, and so it's useless in one sense. So if you look at the Fmax plot against technology nodes across multiple technologies, so there is silicon CMOS, which is the blue dots. The silicon CMOS is essentially all your cell phones, processors, laptop, all the technology that you're dealing with your daily lives, and basically silicon CMOS. Gallium arsenide and indium phosphides are 3.5 devices, much higher mobility. So you can see that indium phosphide technologies are somewhere up there, beyond 1,000 gigahertz, right? So indium phosphide device can amplify signals up to 1,000 gigahertz, but silicon CMOS is somewhere in the 300 gigahertz range. So what do? And this is not actually improving with scaling. So it turns out that this is hard to overcome, right? So how do I use silicon devices to still be able to generate useful amount of power and make systems worthwhile in these frequency ranges, given when you compare one device to one device, silicon CMOS is very weak compared to a 3.5 device, either gallium arsenide or indium phosphide. So how should I think about the system, right? So the idea is basically this, right? So this is your silicon device, which is very weak. This is your 3.5 device, which is very strong. And the question is, this is a pretty non-uniform battle. We know who's going to win. So what can I do? What is the design approach in silicon, right? So the design approach in silicon is integration. You don't have one transistor. You have 100 million transistors in 1 millimeter square. So you need to leverage that capability of using multiple transistors and integration capability of transistors and harness their collective strength. And so I'll try to give you examples of how we do that in the systems. So that's the first problem. Device limitations is the first problem. Second is, how should we think about architectures? Now, typically this is one, classical terahertz architecture, which is some low frequency, then you have a power amplifier, then a harmonic generation, some filters, some mixers, some matching networks, some antennas. And how is this system designed? Well, someone's going to design the antenna. Someone's going to design the mixer. Someone's going to design the filter. Someone's going to generate the PA. Someone's going to design the VCO. Someone's going to generate a mixed signal digital to analog block. And then all of these things will be brought together and connected. This has actually worked well in low frequencies, right? All your wireless transceivers are designed in this way. But the point is that because your devices are so weak, this may not be the optimal approach. Because what you have done here is connecting between sort of digital bits to electromagnetic field. You've basically decided that, well, to connect digital bits to electromagnetic fields, I need these subcomponents. And to design the subcomponents, I need these blocks. And so let's design these blocks and connect the system together. But there could be other ways of connecting these digital bits to electromagnetic fields. And that may not look like these blocks that we have sort of used for decades. And that is very important because your individual devices are so weak, we cannot be operating in a suboptimal space. And so what are the other ways of connecting bits to electromagnetic fields that do not look like a system like that? Are there other ways of doing it? And how to even think about it, right? So we'll try to give you examples of that approach. Now, if I dig into a little bit deeper, and if I say how we design any system, and some of you might be working on passive structures. So essentially, if you're in a high frequency system, this is what you do. You have passive structures. These are antennas, inductors, capacitors, transmission lines, matching networks, all kinds of things. Hybrid couplers, directional couplers. You would design these things. And someone's going to design the active devices, right, with transistors. So these are your passive structures. This is your active structure. This could be amplifiers, mixers, things of that nature. And you would take these individual blocks and connect them together to a system. To do what? To do the system. And what does the system do? Basically connects digital bits or information to electromagnetic fields, if it's a transmitter, or if it's a receiver, connects electromagnetic fields to information. The question here is, are there other ways of doing it? So let's just focus on the passive structure itself, and let's think about it for a while. Now, if you think about passive structures, the approach to passive structure design is use fundamental elements, like the unit elements, and then build bigger components with that. So as an example, you have antennas, you have transmission lines, inductors, and capacitors. You use a combination of these four things and then change the geometry to create different kind of structures. So as an example, if you want to make a quadrature hybrid, right, and hopefully people in the microwave engineering would know this, you can take four transmission lines, connect them like that, and you make a quadrature hybrid. Or you can make a directional coupler that'll do exactly like a quadrature hybrid. However, if I just connect four identical transmission lines, you will not be matched. So what do? You change the width. You change the width, changing the characteristic impedance, and so on and so forth to create a known S parameter structure. For a directional coupler, you need to bring them together. So you bring them together, change the width, and that's what you do. If you want to make a ratless coupler, well, you connect them like that, and then what do? You change the width because you want this to be a high impedance structure. If you went about broadband matching, well, you connect several things together, you change the width, change the spacing, and you can create different kind of structures with different S parameters, right? You can make broadband pass filtering, broadband matching, transformers, antennas. So this is an example of a circularly polarized antennas. It turns out if you connect, cut those edges, it becomes circularly polarized. If you need a broadband circularly polarized, you basically cut a slot. So all you are doing here is we are limited by the fundamental transmission lines. You're changing the width and the length, and the design space is limited by the unit element. But who says that if I wanted to create a quadrature hybrid, it has to look like 4 transmission lines connected together. Are there other structures that do that? Are there other structures that, if I look at it, I have no idea how it does it, but it does it better than a quadrature hybrid? And should we think about systems in that fashion? So as an example, so let's take a quadrature hybrid, right? So it's like a rat race coupler with 4 ports, and so this is not quadrature, this is a rat race coupler. So it's a 180 interface. But this is essentially, think about this like a metal structure, right? It's a metal structure on the ground plane, the metal structure on the top plane. But are there other structures that are just complex to look at, but that can do the same functionality and perhaps better? What are the trade-offs in terms of bandwidth, fabrication capabilities, and so on and so forth? And how should we think about creating such a structure that is different from this one? If you fundamentally think about it, all we are doing in the structure is filling up certain places with metal and certain places with dielectric. And this essentially could be mapped to a pixelated structure where all of these places are metal and these inner spaces are dielectric. And so the question is, are there other structures that do that? And if you could do that, then imagine the range of possible connectivity and the possible structure that can open up. If I think about this structure, like the whole structure, like a 3D pixelated volumes, and you're just filling up metal where you need to be, imagine the range of possible structure that can come out to be. And this is already happening in some degrees in other fields, like photonics, for example. They're coming across structures which are much more complex looking, but actually do much better than classical design, because you're taking the unit element out of the picture. You're not limited by a notion about a transmission line being a unit element. So, the idea of breaking that unit element has been there. It's not a new thing in engineering. I mean, it's not a new thing in arts as well, right? So, for example, if you look at an example of art, people in the Renaissance used to make realistic figures, right? So you try to make your figures as realistic as possible. But then, 20th century, Cubism hits, and then Picasso says, well, I don't care about any of these rules, right? I would just make whatever I feel like in terms of the nose can be connected with anything. And suddenly, a range of new options open up in terms of what paintings could do. It happens in cricket, right? So a classical, this would be Pujara making a difference. So if you think that these are the only shots you can make, and then you're limited by those shots, well, then that also limits what you can do on the field. But if you try to invent new shots, it's basically how you connect the bat with the ball. A new range of shots open up. And I'll try to show you that in some of the structures that we saw, these are very non-intuitive structures, but suddenly they start to have properties that you couldn't do before. So the idea is the following, okay? I don't know what the structure looks like, and I will have some algorithm to create the structures, but it is embedded in a chip whose dimensions is of the proportional to lambda, right? So at these high frequencies where you're terahertz, your wavelengths are the order of millimeters. So that's important to think about. This is the unique spectrum, because in radio frequencies, your wavelengths are of the order of centimeters and foot, much larger than the chip. At optical frequencies, your wavelengths are much smaller than the chip. Only in sort of the high frequency millimeter wave and terahertz, you're creating a space where your chip size becomes comparable to lambda. And by Maxwell's law, when chip size becomes comparable to lambda, you are in a different scattering regime. Okay, and exploiting that with the capability of integrating multiple devices into the chip, you suddenly come up to a space where we can think about designing systems in a completely different way. So I'll show you with THz sensors and sources how that design approach allows you to create structures that think about connecting the electromagnetic fields to the radiated fields, but the structures do not look like classical structures that you know about. Okay, so with that being I would say the new paradigm, let me give you some examples, right? So let's start with programmable THz sensors. How do you make THz sensors programmable? So people have been working on THz sensors for a while. This was, for example, one of our works in my PhD back in there, and we were making these 280 gigahertz THz cameras. So you can see a 4x4 pixel silicon chip THz camera. It's embedded in a sort of can connect it here. You can use this chip and you can image things inside a soft toy because these waves penetrate. So what we did was we basically bought a bullet and a knife and then put it in a soft toy. This is the image from the terahertz, right? This is the image acquired by this chip. But this is a classical, sort of antenna connected to a detector at terahertz. Now, one thing to notice is at these frequencies, the wavelength is so tiny, the antenna is inside the chip. Okay, so that's a critical point. The antennas are now part of the chip. It's not packaged outside. Now, there's not just one antenna. There's 16 antennas here directly embedded into the chip. From 300 gigahertz, we've gone to 3,000 gigahertz. This was a work that we did a couple of years ago, which is putting a 100 pixel 3,000 gigahertz imager in a sort of a single chip terahertz system. And then this was from Berkeley that was doing wireless communication at 240 gigahertz. So these are what I would say still classical receivers. So you have an antenna connected to a detector and so on and so forth. Let me give you an example of the approach that we were trying to tell you about. And the idea is the following. Here we wanted to make a spectroscopy chip. And what does a spectroscopy do? It turns out that many molecules of interest have spectroscopic signatures at these frequencies. And so how do you detect spectroscopy? So the idea is that you shine a wave, these molecules resonate, and when you and the waves that come out of these molecules, or the sample per se, would have signatures of resonance in this frequency range. And so how do you detect that? Well, you have to capture with an antenna, and then you build up a spectrum analyzer after that, right? You might have used a spectrum analyzer in your lab. It is basically a signal that is mixed down across multiple frequencies. And so essentially, if I want to have a broadband system from, say, gigahertz to terahertz, so the signal here spans from gigahertz to terahertz, you have to generate a signal to which you mix it down from gigahertz to terahertz, right? So essentially what you have to do, if you think about a spectroscopy system, you need to be able to generate on chip essentially a signal source that covers from gigahertz to terahertz, and nothing like that close to exists. It's extremely difficult to generate any kind of tunability in PLLs. And so to cover gigahertz to terahertz is just not going to happen. So what we started thinking about is the following. We don't have the source, but we have the antenna. The antenna is tiny enough. The antenna is part of the chip. So what if we start thinking about extracting information from the antenna itself? Are there ways of doing that that can eliminate the entire structure after that? So the initial idea was the following. Again, the idea, the antenna is on the chip, and we have 100 million transistors. What can we do? So the idea was, when an electromagnetic wave, that is very classically known, it strikes an antenna, it creates a current distribution, and the current distribution is unique to the spectrum. Typically, we throw away the current distribution. We don't think about it, right? You take the antennas from the middle, the signal from the middle. However, because the antenna is now on the chip, you can start getting spatial distribution information of the terahertz wave on the surface of the antenna. In a way, you can measure these dynamics in real time with detectors on the chip directly. And so if I could measure this 2D current distribution on the chip, can I then do signal processing at the back end to get the information? So this is what we did. So I'll not go in details here, but the idea is the following. This is a classical log periodic spiral antenna, nothing interesting about that. However, the interesting part is that there is no signal coming from the center. So in a way, it doesn't behave like an antenna. However, it behaves like an antenna cum scatterer. So the signal goes and strikes the surface. It creates a current distribution. And these blue squares, or all these squares that you see, are places where we are measuring the real-time magnitude of the current. So in a way, the incident power gets distributed on the surface, and the detector distribution collectively absorbs the power. So instead of a classical antenna where all the power goes to the one port, here the power goes to 84 ports on the antenna. And so from that sensor measurement, it turns out that you can extract the spectrum information through some signal processing. So you turn your sort of complex spectroscopy problem into a linear estimation problem where your spectrum is unknown, this matrix is known, and your sensor is known. So your sensor is known, your matrix is known, all you have to do basically an inverse of this, right? Well, you can't really do an inverse because of noise and other things, but I'll not go in details about that, but it basically turns into a linear system of equations. And so this is actually the chip. You can see that this is very tiny, 2.6 millimeter by 2.6 millimeter by 1.9 millimeter. The antenna is again on the chip, but unlike an antenna, there is no signal from the middle. The black dots are the 84 detectors that directly connect the antenna and are converting the incident current distribution, impressed current distribution, into a local voltage. And so we get 84 local voltages from the antenna, and we signal processing them. We basically do inversion and things of that nature to estimate what the incident spectrum is. Does it work? We measured from 40 gigahertz. Now think about it, 40 gigahertz to 990 gigahertz, not megahertz. So it's like close to 1 terahertz, right? Close to 1,000 gigahertz. So as an example, when we excite it, say 66 gigahertz, and we measure the spectrum, and we calculate the incident spectrum, you can see the incident spectrum and the estimated spectrum are directly on top of each other. We do the same thing at 918 gigahertz. The blue is the incident spectrum, 918 gigahertz. The red is basically the estimated spectrum, very close, not in the power, but at least close to frequency. We have done it from frequency from 40 to 70 gigahertz, multi-harmonics, 300 gigahertz, wideband frequency ranges. But think about the entire structure. This is the whole chip. There's no yellow source. There's nothing externally, except there's only an antenna, a lot of detectors inside the chip, burns less than a milliwatt of power, right? And it essentially covers frequency ranges from 40 gigahertz to 990 gigahertz. And then we started thinking about, how do I make this programmable? So this was a Nature Communication paper, 2019. So how do I make this programmable? Now think about, how do I make anything programmable? Well, the reason that all electromagnetic structures that are resonant operated within certain ranges is because you have electromagnetic resonant modes that is defined by the shape of the structure and the boundary conditions. But now, since I can measure these near field at at sub-wavelength scales, I can also program the near field at sub-wavelength scales. I can program the modes of the system, and I can design the electromagnetic structure and the circuits in a co-designed fashion. So this is one point I want to try to make. Your antenna design is not anywhere separated. You're not making a 50 ohm interface antenna anymore. This antenna is a complex connection of the multipole scattering structure with the circuit structure. So they are part of the same design. So students who are working in the field have to know everything. And we basically said, well, now since we can measure this, we can manipulate it. So now these detectors have a little bit of programmability. They can change capacitor banks and change the local conditions. And so what we were thinking about was the following. If I want to receive something at, say, 300 gigahertz in a broadside, I will have some programming of the detectors. If I now want to receive the beam at a different directions, I can then program the modes of the system. I can then program the impressed surface current that is optimal for reception, or at least close to optimal for reception at 300 gigahertz, by changing the digital configuration of the detectors. If I change the digital configuration, the near field changes, everything changes. And so if I could change an angle of incidence, I can change against other properties of the electromagnetic fields, and that's frequency, and that's polarization. And so the idea is, can I map these complex digital configurations to incident field properties in frequency, polarization, angle of incidence? So if I know my frequency, polarization, angle of incidence, I just choose the right digital state. So this is a little complex because I'll show the picture of this chip. So this is the same sort of scattering structure, but now we have 16 detectors. Each detector has 5 states. So that's 5 to the power of 16 states. That's 152 billion states. It's a lot of electromagnetic states. So all I have to do now, choose the right electromagnetic state for the given incident field. And so this is a pretty complex because it's very non-convex space. So I'll not go in details about that, but there are mechanisms to at least reach, may not be the global optimal, but close to optimal in terms of the incident field. Does it work? It actually works. So let me show you one example here. So suppose you have the detectors, they are different colors. And And if I choose these particular settings or the colors, you see I have a radiation beam at 300 gigahertz. However, if I then now change the colors to different color settings, you see that the beam at 300 gigahertz is now become bad, but now your red beam, which is at 750 gigahertz, is becoming optimal. So this is just an example showing that the distributed reconfigurability of the electromagnetic structure is making a direct impact on the sensor response across frequency. And these are some measurement results across frequency from 260 gigahertz to 990 gigahertz. And you have large enhancement of responsibility that you can see. So essentially what you can do is take this system, the chip, it works from 100 gigahertz to 1000 gigahertz. If I know the angle of incidence, polarization, and frequency, I can just program the right digital states and it'll be optimal, close to optimal at those frequencies. So now you can imagine that you can start thinking about the systems in very complex environment because it's adaptable. So let me just show you a little bit of programmable THz source and the talk. On the source side, what we want to do? Well, we said on the source side, we wanted to say, what is the field that we want to generate first? Not what antennas are, but what is the electromagnetic field that we want to generate? And then the question is, can I calculate what is the optimal surface current that I need to generate on the surface of the chip? So again, the details are in these papers, but we basically found out that if you have traveling wave current surfaces on the chip, okay, multiple of them, which are spaced in particular modal wavelengths, if you could sustain these traveling wave currents, it would be a very nice radiation pattern because the surface waves are canceled. But antennas don't typically have traveling wave surface. So you have to think about new antenna structures, not just new antenna structures, new electromagnetic structures that can synthesize those currents. So I'll not again go through this, but you can see that this is a structure. These are two transmission lines, differential transmission lines that are connected with multiple transistors. And so what happens is the following. These transistors are connected in such a way that when you just put some DC voltage to this structure, you have a sustaining traveling wave oscillation at 150 gigahertz. These two lines start behaving like a transmission line. So basically a 180-degree current out of phase. However, as this wave is traveling on the surface of the 150 gigahertz structure, the transistors are nonlinear. So it's going to impinge second harmonic into the current source. Now, so 150 gigahertz is going to get converted to 300 gigahertz. Now, because it's a differential transmission line at 150 gigahertz, the phases are 0 and 180. So at 300 gigahertz is 0 and 0. So now you have at 150 gigahertz, you have opposite phase currents. So that's a transmission line. There's no radiation. But at 300 gigahertz, the currents are in phase. So they're going to move in phase on the current. So the same structure that behaved like a transmission line at 150 start behaving like an antenna and radiator at 300. But it is not fed at one port. You're not feeding a 50 ohm interface. It is self-generated. So it's basically converting a DC voltage to radiated power at 300 gigahertz simultaneously. So it's a traveling wave oscillator at 150 gigahertz, a filter at 150 gigahertz because it doesn't radiate, but a harmonic generator at 300 gigahertz and also a harmonic radiator at 300 gigahertz. So that's what I mean by thinking about electromagnetic structures that just don't do one thing, but coming from the fundamental current calculations and thinking about circuits later. And so we build a 4x4 phased array transmitter at 280 gigahertz because you can take one, and so that's one, and then you can synchronize with 4x4 array with central field. And this was like a first to close to 300 gigahertz phased array ever in any technology. So you can do electronic beam scanning in both directions. You can see the chip here. Everything is basically digital programmability. That's it. And EIRP is pretty nice, 10 milliwatt power at 280 gigahertz. And so this basically demonstrated the structure. And so this is what I was trying to emphasize, that this structure does not look like an antenna connected with a transmitter, connected with a harmonic generator. It's all of these things at the same time. And so you can start thinking about new structures like that. So this is a new paper that came out last year at ICCC, where we exploited how metronomes synchronized on a mechanical table. Like if any of you play guitar, you use metronomes. And if you use multiple metronomes, they are close to frequency, but not exactly the same frequency. But if you put on a mechanical table that moves a little bit, they will mechanically couple together, and after a while, they will all oscillate in frequency and phase. So we did the same thing, electronic version of this, in a 4x4 array, radiating at 416 gigahertz. This is the 416 gigahertz phased array transmitter, again with record power from a single chip. Then what we did was we demonstrated another structure where we can not just generate one frequency, but you can sort of spectrally shape what is the waveform that's coming out of it. So you can actually control the delay of each of these waves and generate a pulse if you wanted, or generate a harmonic wave if you wanted. Basically create a sort of a programmable spectral programmable source. And this is a recent paper that just came out as a cover article in Nature Electronics last December 2020. And this was a programmable terahertz metasurface. And so the idea here is that we take one chip, and as a Lego piece, we can make larger scale metasurfaces. But each chip has multiple square rings. Each of the square rings are programmable in terms of their scattering properties. And if you could program this in scattering properties, you can essentially create arbitrary amplitude and phase at the output. So you have the metasurface. Again, they're hardly dissipating any power. The wave comes, and you can create arbitrary amplitude and phase distribution. So as an example, you can create electronic beam scanning, right? You can get the beam moving in different directions. This is at 300 gigahertz. Or you can create holographs. So what we did was we projected P as in Princeton and U as in university. This is measured data at 300 gigahertz projected from the chip. So we programmed the scattering nature of the surface. We projected a P, and then reprogrammed it to project a U. This is, you can't see this holograph. You have to measure it, right? Because at 300 gigahertz, your eyes are not visible, at least most of us. And so, you can program this, but it just basically shows that you have complete amplitude and phase control. This is the ultimate projector, right? This is you can program it to near field, far field, and so on and so forth. And this is another work. So once we started thinking about, okay, you can program this arbitrarily across space and time, what else can you do? So this was a paper, again, ISSC last year, and hopefully it's going to come out in Nature Electronics again. It's the idea that we want to create a secure link between Alice and Bob, but anywhere else, the constellation is completely garbled. So Eve, who's sort of listening to a side lobe, gets a complete garbled information. So essentially physical layer security between Alice and Bob. This doesn't happen in a phased array. If you create a phased array, if Bob receives a constellation, Eve receives exactly the same constellation. But here, the constellation is completely garbled. Again, this was done at 71 to 76 gigahertz. We did the chip, and you can see the series fit patch antenna arrays. And we measured it, and I'll show you some measurements. So for example, in a phased array, if you want to send the data to 0 degree, well, you get the QPSK, nice constellation, but the side lobe exactly at the same constellation. Here, where you wanted to send 0 degree has a nice constellation, but side lobe has completely garbled constellation. Okay, so this is what we call the physical layer security. Again, the details are not there, but the idea is the same. It's basically you're mapping, you're being able to create arbitrary amplitude and arbitrary spectrum in space. And this is again the recent work which just came out in 2021, where we are using the ability to create arbitrary spectrum is to create a terahertz prism. What does a prism do? You shine light and it sends different light wavelengths to different directions. So here we create an active terahertz prism where we send different kind of spectrum in different directions. And the idea is that if a wireless node is located, just by looking at the spectrum, I would know where it is. So it's like a local GPS, if you will. By measuring the spectrum of the receiver, I know where so you can imagine like a warehouse where like robots are moving. You can imagine that all of these could be localized immediately by measuring the spectrum, right? And so we did it from 360 to 420 gigahertz. Again, a completely integrated chips with leaky waveguide antennas, fully integrated transceivers to be able to do that. So again, these are all different applications. Localization is different from physical layer security, but all of these come from the fundamental idea that you're trying to control spectrum, polarization, and spatial field distribution in space, but they translate into different applications. So this is just a I hope that I have been able to convince that thinking about these systems in a different way allows you to come up with new architectures, but also new applications. So I wanted to end by thinking about giving you this one last picture. That don't think about that you're limited by these functional blocks. Think about the holistic system from end to end, from information to electromagnetic fields, from electromagnetic fields to antennas, and think about how you can connect those things in ways that are different, enabling you new functionalities that you couldn't do before. So with that, I would end with the last couple of quotes. And I think this is where you need to think about outside the box, right? So I really like this quote, and this is actually used by DARPA as what they call the difference between evolutionary versus revolutionary R&D. So this was a New York Times article in 1903, and they were basically in 1903 they were projecting that they were thinking about flying machines at that time, right? So New York Times article says, it might be assumed that the flying machine, which will be really fly, might be evolved by the combined continuous efforts of mathematicians and mechanicians in from 1 million to 10 million years. So basically saying that, this is not going to happen. On their diary said, we started building. So with the ability to sort of challenge, notions or sort of well-established notions allows you to make those quantum leaps, right? I think that's really inspiring. And if you think about most of the inventions that have happened in the world, they were challenging, sort of well-established notions. And I think in whatever work that you're doing, it's important to think about, rethink sometimes, take a step back and rethink the whole problem. And suddenly you would see sort of newer ideas coming into the picture. So always push your boundaries, right? And learn things that you typically won't learn otherwise. So if you're working on antennas, try to think about what else is connected to an antenna. Try to think about other things, right? Transceivers. And you will see suddenly opportunities that are coming out that you wouldn't do otherwise. And don't have any fear of failing. I think that's something that we often do. For example, if you go back to the first millimeter wave work in the world, right? It came from Calcutta, right? I mean, I don't know if you have seen these things, but the ingenuity of the work, it's absolutely mind-boggling, incredible, right? Working at 60 gigahertz in 1890s with materials and things that are just hard to think about it these days it requires an absolutely out-of-box genius invention, right? So these, for example, the jute strings, I don't know if you know this, but these are polarizers. I mean, these are essentially rotators, polarizer rotators. I mean, this is basically a book where slits are cut to act as polarizers. Now you can buy these things at high cost. But at that time, they used to make these things. So you really need to think about what has been done in this field in a more holistic fashion. But don't be limited by what is available and imagination. Don't let your imagination be limited. And so I really like this quote, and this is basically a motto of a lab, which is, reasonable people adapt themselves to the world. Unreasonable people attempt to adapt the world to themselves. All progress, therefore, depends on unreasonable people. And so be unreasonable and don't fear failures. With that, I will come to the end, and I will just show my picture again of the lab, and we'll be happy to answer any questions. Of course, I have to acknowledge my sponsors. Happy to answer any questions you might have. Thank you so much.
Thank you, Dr. Sengupta. It was a very interesting and informative presentation, and at the end, it was also very inspiring. So if there are any questions on behalf of the participants, I think they can unmute and ask the speaker themselves.
Hello, sir. This is Ardhendu Kundu from Jadavpur University. So I have a small doubt. That is for the reconfigurable, means for the antenna, log periodic antenna, you told that we can try to get the information of the spectrum from the n number of ports. Right, sir. So how can we extract the polarization information as well? Means I just want a little bit more detail.
Yeah. Good question. So there's Catherine. So we were thinking about a spectroscopy system, right? So let me see if I could put this up. Okay. So in that particular work, let's see, go back here. Yeah. So the current distribution is a function of few things, right? One is angle of incidence, the spectrum itself, and polarization, correct? And so in a spectroscopy setup, this is not a spectrum analyzer, this is a spectroscope, which essentially means that you know what your angle of incidence is. It's sort of a control environment, right? And you also know what your polarization is. So all you don't know is what your spectrum is. And so given the fact that you already know the angle of incidence and polarization, you collect the spectrum. However, if you think about the way it works, it's basically having some unknown information being mapped to a space of current distribution. If your unknown information is also polarization, then you have two orthogonal axes that you have to find out, which essentially means the number of variables on your system has gone down. So your resolution in frequency would probably go down. Does it make sense? You're basically trading off one with respect to the other. But in a spectroscopy setup, you typically know your angle of incidence, which is broadside, and also polarization.
Okay, sir. Thank you. And sir, another little doubt, that is whether we have some pre-installed data on the system before making the actual evaluation of the spectrum and polarization.
What do you mean pre-installed data?
Means this will be the current distribution. This will be the current distribution if this particular frequency and this particular polarization is incident on the antenna. Or
yeah, exactly. So what we do is initial calibration, right? So let me go back here. Let's see. So if I could show that. So you see that here. So what are we showing here? So this is 40 gigahertz to 990 gigahertz. And these are the detector response at different frequencies, right? So you basically get this matrix, right? So you have to calculate this matrix. And the matrix is a function of your scattering structure, your boundary conditions. You can simulate this, but it's better to measure it once, right? And it's constant. So this matrix is this current distribution at these individual frequencies. Once you get that current distribution in individual frequencies, you know this scattering matrix. You are getting the sensor information from the incidence spectrum. You do not know this incidence spectrum, and so that allows you to calculate this linear relationship.
Okay, sir. Thank you so much, sir. Thank you.
Sure.
Okay, so there is one question which is written in the chat box from one of the participants who asks that how much is the gain for the THz sensors that you fabricated?
So the THz, as I mentioned, the gain of a single transistor at these frequencies are very low, right? So if you're talking about 100 gigahertz, you can get a 4 or 5 dB gain. If you cascade many of these, you can get 20 dB gain. But the point is not gain per se, right? So the point here is, are there other ways of extracting information that you couldn't do before, right? So again, you're not comparing this with an idealistic or an amplifier that doesn't exist, and it doesn't even have a LO source. So there's no real way to connect like a gain, but I wouldn't even think about this as a gain system. I'm not building an amplifier, for example, right? But if you try to build amplifiers at say 300 gigahertz with silicon, you will not get any gain. As I mentioned, Fmax is sort of close to 300 gigahertz. But if you are thinking about, at 100 gigahertz, you can get gain from these systems if you're thinking about classical transceivers.
Okay, so I have a question. As the frequency of the wave increases, so we know that the energy which is E equal to H into F, it tends to increase. So is there any effect, or has there been any study about the effects of very high frequency electromagnetic waves on humans or on living beings in general? Because like 50 gigahertz or 100 gigahertz, close to terahertz, the energy of the electromagnetic wave will be a bit higher than normal communication systems.
Yes, but the energy of the photons is so less, it really doesn't matter. And this is, if you think about what you care about is power density per area, right? So essentially power density, watts per centimeter square. And there's empirical studies. For example, when you create your cell phones, right, you still have to maintain those limits, and those limits are of the order of 10 milliwatt per centimeter square for low frequencies. But the idea is that there's nothing fundamentally has changed from radio frequencies to even frequencies above 100 gigahertz, because your photon energies are so small compared to what you need to have any kind of disruptions. For example, in optical frequencies or even say X-ray frequencies, where you need a very high, you get very high photon energies. I mean, these are very, very tiny photon energies. So nothing chemically is going to happen. All you care about is whether your tissue is heating up, if that's the question, right? And your tissue heating up would be the same way as tissue heats up in a microwave or in a cell phone, for example. So that's why there's like safety limits on how much energy you can have per centimeter square.
Yeah, I think I get your point. So there is another question from one of the participants. What is the prospect of high mobility 2D materials to obtain high Fmax and cutoff frequency for terahertz detection?
That's a good question, actually. So, and people have actually looked at graphene for a while. 10 years ago, there was a lot of work on graphene trying to enhance mobility and so on and so forth. So but it hasn't gone too much. And the reason is that, at the end of the day, you can make one transistor with, high mobility. But if you can't make 1 million transistors with high mobility in a single chip, it's not going to be, no one's going to use it. And so what has happened is there's been other ways of enhancing Fmax. So currently there's already a project of trying to make silicon germanium transistors cross 700 gigahertz Fmax. And if graphene can do that and silicon germanium can do that, then people would take silicon germanium because, again, the integration ability is unmatched. That being said, there's still a lot of work happening on the 2D space with high mobility 2D materials. And it is possible that new transistor architectures would emerge from those things. The science is a little unclear. I think that's a lot of work that's happening, and a lot of work needs to happen. But the initial work on just to use graphene to enhance mobility, to make faster classical transistors more faster. While it was demonstrated and results came out, commercially it hasn't gone too many places. However, there's a lot of interesting work happening in 2D materials. But graphene is not the only 2D material. There's, molybdenum, disulfide, MOS2, and things of that nature. That's also very interesting.
Okay, thank you for your answer. I don't think there are any more questions in the chat box. So I guess.
So there's a question on THz sensors and how about THz wireless communication.
Oh yes. Sorry, I missed that. Yeah.
So it's actually a good question. I actually had a paper, and I would encourage you to write about it. And the paper is called is titled. What is the title? It's called Integrated Circuits Above 100 Gigahertz. Are we there yet? And that paper actually calculates that currently, with the current state-of-the-art technology, you can make backhaul links for wireless communication with reasonable energy efficiency at 100 gigahertz, close to 200 gigahertz. And that's doable. People are already making these things at 140 gigahertz and so on and so forth. So this is possible. However, if you try to push it beyond Fmax in a classical transceiver wireless systems, and we made a calculation at say 1 terahertz, that we don't have the transistor technology to be able to do that. So in certain applications, you're limited by devices. In what I presented, you're trying to come up with creative ways of overcoming device limitations. But if you're thinking about classical transceiver systems, there's no way of overcoming the noise figure in a penalty that you would get as a result of no gain.
Okay, so there is one more question. Which kind of terahertz systems for integration of antennas on chip? What are the bias considerations?
Great question. That's exactly the point I want to make. There is no matching network. That antenna itself is a distributed matching network. So let me just show you the screen here. Can you see it? Oh, no.
No, not yet.
Hold on 1 second. So if you look at this structure here, there's no matching network. The antennas is directly connected to the transistor. So the way the transistor, the detector positions is determined is that antenna, through its distributed structure, is behaving like a quasi-scattering plus a matching network structure itself. And so this is what we're talking about. You should not be thinking about have an antenna with a matching network, with a detector. If you think about partition ways, the losses and the range of functionalities would be very, very limited. We are thinking about a single structure that does multifunctional electromagnetic behavior. And in this particular case, the antenna itself is a matching network.
Okay. So I don't think there are any more questions.
Okay,
So,
great.
Yeah. Thank you for a very informative session. Thank you for taking the time and interacting with us for such a long period of time. We really appreciate it. So,
Sure. Absolute pleasure. If someone wants to, I can hang out for a while. So if someone wants to chat a bit further, that's fine as well. I probably have to leave in 15 minutes, but if someone wants to chat in 15 minutes, I'll be more than happy.
Yeah, actually, we have our treasurer, Shami Pendu Das. She's actually a very bright student. And he was asking me the other day, that what he needs to do if he wants to do a PhD from Princeton. So what does he need to, where does he need to apply, who does he need to talk to, and stuff like that. So maybe you could clear it up.
Well, I mean, there's an application process. So there is a PhD for 2022 opens in December. So it's a highly competitive selection process. So the only thing that works is you apply, and then there's a selection process after that.
Okay. So I'll let him. I think he left the meeting because of some issues. So I'll let him know. Pass the information on. And one thing the participants were asking was that is it okay if we share the slides, or is there any problems with respect to that?
Do you have the slides?
No.
Oh, okay. So let me see what has been published or what has not been published.
Yeah, no problem.
And then I'll send you the slides. Just send me an email and I'll send you the slides.
Yeah, okay, no problem. Okay. Yeah. So, how long have you been working in this field? Since your PhD? Like, from which year?
You mean the field of high frequency circuits and systems?
Yeah.
Well, I did a PhD there on Caltech, and we work broadly in these frequency ranges. So it's been, I would say, more than 13 years now. Yeah.
Oh, nice.
Nice. Yeah.